All right, let's talk about these. So the flute or the gullet is the area that's back there to contain the chip. The land or the margin is the little polished area that follows the cutting edge all the way up. What is the purpose of the land on a drill bit? And if you look back at the picture of your end mill, there is a very similar thing. Is it for the same purpose or a different purpose? It's just the little part that's ground though. There's a little width that's ground that goes all the way along the cutting edge all the way up. Is it there for the same purpose or a different purpose than the end mill?
I don't think it's very much of cutting. It's the cutting happens with the tip. So it seems to be maybe along the pulling the chips out to make sure it just goes down the hole in constant concentricity.
Yeah, so it is a different thing. In both of them, it is the area that they use to sharpen that edge, just so that if there are any chips there, it will cut them loose. But on the end mill, it is ground in there to give a little bit of clearance so that the cutting edge doesn't rub on the right behind the cutting edge doesn't rub on the hole or the material that you're cutting and heat up and wear the cutting edge out. In a drill bit, it is for guiding the tool. So the attempt is to guide the tool on the hole that you've already drilled, which has the effect that you would expect it to have. If you drilled a straight hole, it will help to guide the tip to go straighter. And if you are drilling an angled hole, it will drill at an angle. And it is amazing how big a turn you can make with a drill bit. So this drill right here could pretty easily walk, I don't know, it could pretty easily walk a little bit less than a 1/4 inch off to the side and drill a hole. And you wouldn't know it. You would just be drilling and it's bending over to the side and going off at an angle. And they're so flexible, they'll just do that.
With insert drill bits, when the actual cutting edge is quite a bit larger and we don't see that the land with concentricity, are we anticipating that the actual shank retains all the rigidity?
Yeah, so in a drill bit that uses inserts, they're typically on bigger drills, and they have a different method of evacuating the chips so that the shaft of the drill bit is not nearly as weak. So if you look at these, this is nearly a 1/2 inch drill bit. It isn't, I can't remember exactly what it is. I pulled it out of one of the drawers that we never use. So it's that size.
It's 15-30 seconds.
15-30 seconds right there. So we rarely use 15-30 seconds. We had a good set of them. They're all sticky because we don't use them very much. But when you look at these, nearly a 1/2 inch, right? 16-30 seconds would be a 1/2 inch. This is 1/32 under a 1/2 inch diameter. What is the thickness of the web when you look at that in the middle? So if you look on the very end of the drill bit, right here, what is this width kind of? Yeah, so it's like 100, 150,000, something like that. So you're taking what you expect, what looks like a big 1/2 inch diameter rod of steel, but it effectively is the same as if you were drilling with something that's only an 1/8 inch in diameter, and this is 6 or 8 inches long. So yeah, they're really bendy. That's a problem. So where is this highly negative rake angle? Did you locate it? Because there are lots of rake angles on the end, and it's hard to tell. Okay. So it is right here. We have the web, this little section that goes across, and that rake angle is right here because at the very beginning of the cut is cutting from here to the center, from the edge to the center of this little line on the end. And that is just mashing the material down. So you're cutting with a super negative rake angle. as soon as you get outside of that, you're cutting with this positive rake angle out here, and life is happy and it cuts just fine. But that little center web is cutting with this highly negative rake angle. So what can you do about that? Well, you can spend a lot more money, and you can buy a tool like this. You can see that it's had an extra grind in here, so rather than cutting with that highly negative rake angle, they've ground around this corner and made it positive. The problem with these drills is that they don't last very long because that little tiny cutting edge is super unsupported down there, and so it will get dull or break off pretty quickly.
When you say ground, is that a secondary finishing process, or is it like
Yes. Yeah, so it is using abrasive, so using rocks to shape the surface, and that's how we make things sharp, is by grinding.
Is that usually done by hand, or does a machine do it?
No, we need to use a machine. Yeah. You could do it by hand, but that would suck. That would not be any fun.
Wait,
Yeah.
so the reason it's an even section is because it'll make it so the tool doesn't wear as fast?
Sorry, say that again?
The reason like the highly negative rake angle has an even section is on the intersection is because it makes it so the tool doesn't wear as
The
fast.
tool doesn't wear as quickly, and this is super easy to do. So when you're selling drill bits, that drill bit that you're holding is probably I don't know, a $2 or $3 drill bit, whereas the end mill that we were holding yesterday or the day before that was essentially the same size is like an $80 tool. So they're going for super cheap here, and so they just give us the easiest one. If you make it a little bit better, this is called a Bickford drill. If you make it better, it's just more likely to fail. But there are other ways that we can solve this too. And some of those are pretty cool. Yeah, drill terminology, that's great. Oh, let's see, I guess the helix angle is the angle right here, angle D, measured from the axis of the tool. So what is that angle? And then the included angle is down here on the tip. So what is that included angle? And we change that based on what material we're cutting. Yes?
Is it measured like from the drill, like from the motor? Like is it the small way or is it the big way?
It is measured this way. The small, is that the small way?
Yeah.
Okay, that's the small way, yes. It is less than 180 degrees. Guess that would be the way to say it. All right, chips. Great. So what I would like you to do in this video is I want you to look for what safety processes are being used. How is this person trying to do this safely? This drill bit has no teeth, by the way. It's a friction drill bit, which is weird.
Does that change
I'm
the
sorry,
power?
the bandsaw is.
Oh, so
doesn't
is
have teeth.
it going up and down like this? The same
Yes,
side to
it's
side?
ripping through there, yes, from top to bottom.
Push stick is genius.
He doesn't have to
He's going away from it.
his shirt is better.
He's not wearing a crop top. Clamp. I bet he's wearing safety glasses.
It's hard to know though, isn't it?
I don't know for sure,
His
but I
beard
hope
is
he
trimmed.
He
is.
actually left his head at home because
Oh,
that way
genius.
you don't damage your eyes or hearing.
I
There's
should
no
do that.
accountability.
You can see his beard.
Well,
It was like full trim.
That's the portion
Gonna
that's
get
glued to
inside.
his neck.
If he had too long of a beard, it would get caught.
Not his face beard.
Go away. I don't want to know this. All right, so what did we see? Using push stick, using vice grips to grab the end, not ever reaching in to move the cut off parts out of the way. Use the part or the push stick to move them out of the way. Wasn't pushing too hard though. With that kind of saw, you do have to push pretty hard because it has no teeth. But anyway, okay, good. Saw like that. Don't saw like Alice. Yes.
What's the point of using a friction saw? Saw teeth?
I don't actually know why he's using it there. There is a rule for bandsaws. And the rule is 3 teeth in the cut. So that means if you're cutting a really thin piece of material, you should have a saw blade that has lots of little tiny teeth. If we're cutting something big and thick, then you can have big teeth on it that can take out material pretty quickly. So when you go in the plastics lab, in the soft tooling lab, and you use the composite bandsaw there, what does it have?
It's like abrasive.
It's what?
Why abrasive?
It's abrasive, yeah, it doesn't have any teeth at all. So it is just rocks glued to the edge, little tiny rocks glued to the edge of the blade, and that's because you're almost always cutting thin materials there, and also it gives it a highly negative rake angle so that it can sever the fibers better. But if you're cutting sheet metal, you need to use a blade that has a lot of little tiny teeth instead of really big teeth. When we're cutting wood that's thicker, we use big teeth. So this probably makes it easier because he's cutting pipe. If you have bigger teeth on the blade when you're cutting the pipe, it will catch the pipe and try to twist it once you've gotten through the outside wall. I would imagine that's what's going on, but I don't actually know. All right, we use center drills a lot. So the point of a center drill is that it's short and it's stubby and it will not walk because the highly negative rake angle on here is tiny. And so it will not walk. You just use that to put a hole in that you use as a starter hole. So when you start with your large size drill bit, it won't walk off to the side because you've already drilled out that little middle section for the start of the hole where it has the highly negative rake angle. Other things that we may need to use. We like to create counterbores and countersinks to get rid of the head of the screw to put it down into the material. And if we're doing those, you can do those with a lot of different tools. You can create counterbores with end mills. You can create countersinks with things that look like this. There are also some tools that will have the drill bit and the countersink all as one. So if you're making a lot of holes and every one of them has a countersink or a counterbore, it will be a single drill bit that has both shapes in it. And then the last thing is reamers. Yes?
Sorry, wait, what do they do? The countersink and bore?
The countersink and the counterbore, the purpose of them is to get rid of the head, or not to get rid, but to hide the head of the bolt or screw. So it's down in the material rather than sitting up on top of the material. And then reamers, we use reamers to make the hole actually be straight, to actually be cylindrical, and to actually be smooth. So the reamer goes in and it clears out just the little chips that are on the edges, things like that, and makes the hole nice. When we want to use a reamer, we cut the hole one size smaller than we're intending for the final hole to be, and then we use the reamer afterwards. You'll notice on the reamer, it's got little tiny flutes. It has hardly any capability at all to deal with chips. And so it can't take very much material. And in fact, we were working on a compression mold last year, and we're having a lot of problems with this because as we tried to ream the holes, it was getting enough chips that they would fall down in the bottom of the hole and get all packed up there and cause our reamers to fail. So anyway, that's gonna be all fixed this year when Keaton tries to do that next quarter, or maybe not Keaton. Luke's doing that, yes. All right. How do we call out holes? There are several ways that you can do it. So this is a reasonable hole call out. This is sort of the long form version. So it says 4796 through. That means we start by drilling a hole all the way through, and then we're going to counterbore, diameter 0.765 by ½ inch deep, and then thread, and then the thread call out is 1/2 20 by 1.5. So a thread call out is mean diameter threads per inch. So the mean diameter is a 1/2 inch. 20 is 20 threads per inch, and then 1.5 is the depth to which it is counterbored, or it is threaded. So how far down do those need to go? So that is sort of the long form version of it. With a countersink, we have something pretty similar. This is not a threaded hole, but we have the diameter of the actual hole and its depth, and then the countersink diameter is what size is it at the top of the hole, and then what angle is it. This is kind of a weird call out to call it out that way. In many instances, this is, well, yeah, it can be called out that way. Yeah, we'll just say that. Now, old school, you would tell the person how to do it. You would say drill 0.4796 through, counterbore to this depth, thread or tap 1/2 20 by 15. New school is that you should just give the whole call out, and so these are similar. This is 1/4 inch diameter hole, 0.375 deep, and it needs to be counterbored. So this little bucket symbol is counterbore, 0.375 by 1/4 inch deep. And so this is an odd hole because it's counterbored 1/4 inch deep and only goes 175 or 125 past that. That would be a very odd hole. But anyway, it could happen if your piece of material was 375 thick and you were bolting it to something else. Just not a lot of space there. You can also, so this is one where it's drilled through and then has a countersink. The little bird beak is a countersink, diameter at the surface and the angle. And then the other two are the same, but it just says to do the counterbore, the countersink on the far side, so you don't have to put in an extra drawing view. So what's different about this from the old school way is that we're not telling the manufacturer how to make these. They can make it any way they want to, they just have to make it fit this. How would I make them know that I want it reamed? Because I'm not allowed to, in the new school, I'm not allowed to tell them to ream the hole. So how would I indicate to the manufacturer that I wanted them to ream the hole? Yeah.
Like put a tolerance on like how straight or parallel it is.
Yeah, so I'd give them a cylindricity tolerance, or I'd give them a straightness tolerance, something like that, and I would make, or a diameter tolerance that was really tight, and then they will have to ream it to be able to achieve that tolerance. Or they could potentially, if it's a big enough hole, they might be able to mill it, but it doesn't really matter to me how they make it. It just, if I want to make it better, I can do it by that. Okay, things you can choose in drilling. You can choose the helix angle. For really soft materials, we'll stand the helix angle up straight so it's axial with the part. And then the harder the material is, the more that we lay that helix angle back. That means it goes through the material more slowly. We can do a bunch of things about the type of drill, and we'll look at that in just a minute. We can change the angle on the end of the drill, which we would do depending on the ductility or the brittleness of the material that we're trying to do. The only place that I've really seen this used is if you're drilling cast iron. People will use a different drill tip angle on cast iron because the brittleness really makes a difference.
Hey, Jared,
Yes.
do people use cast iron for things other than?
Cookware?
Yeah.
Yes, there's a lot of stuff that's cast iron. So especially all old engine blocks were cast iron. Now a lot of them are cast aluminum, but not for diesels. They're still cast iron for that. Cast iron is inexpensive, so as long as you can handle the weight, if you need something that absorbs energy and is good in compression, cast iron is good for that. All right, weird things about drills. This is really annoying. In the Freedom unit system, there are 4 different systems of drills. The first is numbered drills, and those are drills that are smaller than a 1/4 inch. And then once you run out of numbers, then you get to lettered drills. Well, and even the numbered drills, you know, they got to 0, which is the smallest drill, and then they go smaller than that. They have aught and double aught and triple aught drills, because they kind of ran out too soon. So anyway, that was a bad call on somebody's part. The lettered drills are between a 1/4 and a 1/2 inch. Well, this is really inconvenient because the letters don't really stand for anything. They're just in alphabetical order. And then there's fractional drills, which are okay, except that fractions are a certain distance apart that may not relate to anything that your hole actually needs. So the one that sort of goes around the whole thing is the decimal series, and so decimal drills list the drill diameter to 3 decimal places usually and can cover all of the other series of drills. It's an interesting system because in the Freedom Unit system, we have 3 boxes of drill bits just to have the set of drill bits that are required for making things in the USEN system. If you do metric drills, it requires, I don't know, it's not very many drills. It's like 15 or 20 drills will get you a very large range of hole sizes, because they just don't have the gradation of hole sizes. They are much bigger gaps between them, and it works just fine. One of the really sweet things you can do with a drill is, we talked about one of the problems being, or 2 of the problems, one of them is getting the chips out from the end of the drill, and another problem was getting coolant to the end. So you can put holes through the inside of the drill bit that go to the end so the coolant squirts out at the very end. But the problem is, if we did that and we put the hole through the web of the drill bit, we'd be taking our really thin, weak portion of the drill bit and making it thinner and weaker. So instead what they do is the hole is in a spiral going down the thicker part of the drill bit. So the question is, how do they do that? And it's really cool. So the way that they do that is that carbide, remember we watched the carbide insert video, and the first thing it did was it swept the little carbide in the hole and then it mashed it super hard, and it was just paste and powder put together, and it just mashed it into the shape. Well, carbide drill bits are made by extruding carbide out the end of an extruder. And so when you shove the material out of the hole from the extruder, if you put slightly, the die that you have that you're putting it through, you make it so that it has a slightly different amount of length on the 2 sides than it does on the others. That will cause more drag in those areas, which will cause the part to spin as it comes out. And so by adjusting how much drag you put on it, you can adjust the rate at which the material spins as it comes out of the extruder, and then you extrude it at the rate so that it matches that, and then they put fishing line inside. They just have fishing line that they feed into this part that they're extruding, and that gets wrapped around the outside all the way to the end. Now, you take this, and you have to fire the carbide. So you take that carbide, you put it in an oven and you fire it, it reduces in size, and it burns the fishing line out of the inside. And then when you take the drill bit and you actually grind the flutes into the drill bit, you just have to line up on those holes on the end to begin your grinding process. And it ends up with spiral holes down the inside. So super cool. Say you wanted to drill holes, you wanted to drill long holes, and you didn't want to have to, or you just needed them to be straight. 2 ways to do that are gun drills and BTA drills. These are things that you don't necessarily see as often. Gun drills are actually very old technology. They were around in the time of creating rifles. So as long as rifles have been a thing, gun drills have been part of the process, or yeah, of making them.
Is that why they're called?
Yep, it is why they're called gun drills, yes, yep, exactly. And so the point of a gun drill is it has one cutting edge, it's one tooth. Yeah, and it has this big L shape, so it is shooting coolant to the end, and then the chips are coming out this L shape that is cut into the bit. So this end part cuts, the rest of it is just a hollow tube that's kind of a circle with an L cut out of it. So you can shoot the coolant down the inside of this, and then it shoots the chips back up the outside. The BTA works backwards from that. It shoots the coolant down the outside, and then there are holes in the end, and it shoots the chips back up the inside. So let's look at those, because it is worth seeing the amount of coolant that either of these takes. By the way, at Caterpillar, we had a guy who used a gun drill, had this giant machine, had 14 gun drilling stations for the connecting rod, and he, it was nasty. It used this high sulfur oil for the drilling process to keep the drills sharp. And so he was down there, Paul, he always had on a Tyvek suit all the time. And he just sat down there and he smoked like a chimney, but you know, there wasn't much you could say about it because the machine also smoked like a chimney. So it all worked pretty well. And you would go down there and it was a loud machine, and he was always wearing earplugs, and he talked about this loud all the time. You could have the hardest time hearing him. But he was incredible with his machine. He would stand there and he'd say, sounds like spindle number 12 is getting a little dull. And you would go, and sure enough, number 12 was getting a little dull. And I don't have any idea how he picked that out of all this noise, but he had run that process so long he could just hear it and know what was happening. He was one of these, so if you are doing something with folks in a shop, so if you have folks who are doing injection molding for you or whatever, one of the things that you'll find is that there's all this urban myth that builds up around a process, and it's really important as the engineer to pay attention to that, because it almost always is indicative of something real, just the misassigned to what causes it. So you'll have people say, well, you know, when I stand on my left foot, this machine works way better. And if I stand on my right foot, it just doesn't make good parts anymore. And you know, you're like, crap, that's not, there's no way, you know? But you go down there and you watch them, and what you'll find out is when they stand on their left foot, they're loading the fixture differently. Or when they stand on their left foot, they're leaning on the machine and it's got a screw loose on the floor that shifts the fixture a little. Anyway, just as you are dealing with things in industry, listen to all those little things. Don't just write them off as that's crazy, but listen to them, because the people who run the process every day know the process way better than you do. However, they often have these crazy ideas as to why this thing is true. So you have to kind of divorce the idea from what's actually happening here. All right, this is the gun drill. No, actually, this is just a through coolant spindle. You can tell that this is a US drill bit because of the music.
Canadian music's so much better.
So when this comes out the other side, look at the amount of coolant that is speeding out when it gets there. That's pretty amazing because the limit that people normally figure for drilling is about 8-to-1 is kind of the limit of normal drilling. If you're in the 10 or 12-to-1 region, you're really doing deep hole drilling. 72-to-1 is pretty nuts. But anyway, you can tell it's a U.S. company because US metal.
Does that mean that it's like that we're like 82 times longer than it is wide?
72?
72.
Yes, the length of cut is 72 times the diameter. Yeah. Okay, this is a gun drill. So remember, gun drills, the drill is L-shaped. Now this is on a lathe, so the drill is staying still and the part's turning, but anyway, same thing. Gun drills usually have to be guided by a bushing at the beginning of the cut. And so I believe that this already has a hole started in it to act as the bushing because the gun drill guides off the part that you've already cut. It's a lot of coolant. And a really big, funny folded chip coming out. But makes really good deep holes. And then the last is the BTA. Remember the BTA, the BTA drill bit, this one actually has two tubes, so it has an outer tube and an inner tube. It is feeding the coolant between the outer tube and the inner tube. It goes down to the end, goes around the head of the tool, and then comes back through holes and through a hollow shaft on the inner tube. And so they will show the drilling for a while, and then they will zoom back to see a vertical column that's attached to the end of the drill. And so look at the quantity of coolant that they are flowing through it when you see that vertical. Okay, break time, then we'll get back to this. 5 minutes, 11:05.
Do you know if that thing uses a traditional ER saw collet? Or how does it like
For driving it? No, for the BTA.
That was a tricky, because when it was spinning, you could see through the little.
Normally it would be straighter collet than that, so like an HSK or something, but I don't know what this is. The whole system, you have to buy the whole system because it's got the feed in and out. So it's got also a lot of rotating seals in there, which are a bummer to maintain. And the inside one has chips flowing through the rotating seal.
And that is coolant from the top coming
Yeah, that's
down,
coolant
flowing through.
Yeah, to that annulus, and then it comes back through the center shaft.
So I have a bunch of
That's why, yeah.
That's cool.
And not super, not used an incredible amount, because, you know, you can't, tool change this thing at all. With a gun drill, they're hard to deal with because they're very long, but you could tool change a gun drill.
Which days I go to bed at,
Yeah, you just
which
go
is
there,
not the
do
time that I
your
should be going to bed,
thing,
and like an upper amount of
It's a
sleep
thing.
for my
Yeah.
9 a.m.
just
class,
add
but
procedures.
I will actually do it. If I say, yeah, I'll go to bed at 11.
I have to register during all that time, so I was like, fuck.
Oh, dude, you'll be fine. I mean, like, it's literally all just classes for us. Like, you'll be chilling.
Sweet.
I was
Design
first
friendly.
yesterday at 4 and I got fuck. I thought tonight it's fine.
Yeah, I'm just gonna build the schedule and then you can like just click register and then make it all clean.
It's gonna be a long Tuesday.
Really? We're doing mechanics and drills. Yeah.
What was the acronym for that kind of drilling just now?
Yeah, I think I'm gonna do that as well.
I'm confused.
And I have no idea what BTA stands for.
That's what I was gonna ask.
Today?
Yes.
No, they're not gonna do that. We don't legit thing. But
Like
like,
the
Was it furry convention?
No.
Yeah, dude,
I'm
so
going to
fast.
Friday.
Oh, yeah.
Fucking hell, dude. Actually, I've never had a day off
Also named Gus.
during the week.
It's nice.
Boring and Trepanning Association.
Was I here?
No, it's in
Trepanning.
Especially winter quarter.
Oh,
Yeah.
Canada?
Cool.
Paper on Friday.
So there we go.
Interesting.
I hope it's good season.
I think it's supposed to be a lot easier. I think it's supposed to be a lot easier.
Dude, if you
Well,
remember
okay,
earlier I was
so
selling,
Yeah, what the fuck?
like, frosted milk, or not selling, but like giving.
That was what I had.
Trepanning
And then it
is
took me like 2 hours to
drilling
figure it
holes
out.
in gulls.
What?
Do they even make frosted milk?
Trepanning is the act of boring holes
Yeah,
in
ice
skulls.
cream is probably.
Oh my god. Proceed.
Yeah.
What are they doing over there?
I didn't actually know that.
Apparently, that's why they call it BTA instead. Instead of highlighting the fact, hey, we're the
Are you
group
doing it
that
too?
figures out how to drill holes in your skull.
Yeah.
I guess I know what it's used for.
There you go. I don't think you need deep hole drilling, and it would be bad to spray that much coolant in your skull. So maybe that's a different drill.
Some form of coolant, not like
Two
that,
words
like
that make
coolant
the
with
most
a giant
sense.
seal
I
across your skull.
can't.
No, cause you're just, well, bone's not very hard to drill,
No, I can do
and
any.
so you don't need it. It smells terrible, when you cut or drill bone, but
I thought it was supposed to smell like Fritos.
Fritos?
I heard somebody say that it smelled like Fritos.
I don't think it smells like Fritos, but.
Hannibal Lecter.
I don't know. I only know internet things. I have never had to drill bones personally.
My brother did rotation
Oh my god, bro.
in that and said that it's really fun. It's like doing wood shop, except that everything's made of stainless steel. But besides that, it's all the same tools.
Oh my
It's
God.
about the same level of accuracy.
We're still in break.
Yeah, I
know.
know. Y'all are going hard at it.
I didn't do anything.
Was that y'all?
My-
Equal teamwork here.
AJ, phone.
Oh, yeah.
You gotta fix
We do it on my laptop.
You gotta fix that. On your laptop?
Yeah.
That's not fair. That's so good. Holy cow.
That should have been a 19.
Hey, no, I stand by this. This is like 3 minutes. I'll be standing by that.
Oh my god.
Wait, what?
Man, that's the one thing I wish I could get retarded.
Yeah, I know, I heard you was the
You can get there though, you're just.
I will. One
Unfortunately,
day I'll,
nothing
I'm
I
just
do
gonna
is private.
quit everything. I'm really gonna draw for my life now.
So you get little practice every day with one way.
That is true.
All right. So we're gonna talk a little bit about grinding. This is kind of a quick skip through grinding, just to understand what grinding does and what it's about. So grinding is the use of abrasives to machine. It is the same chip forming process, except that we're not controlling the cutting edge. So that's the big difference, is the cutting edge gets broken and reformed all the time. So we have a ton of little pieces of material, this abrasive material. It might be garnet or it can be diamond, just something that's very, very hard. And we position this somehow. Sometimes we do it in a slurry, sometimes we will put it in something like a wheel, and then sometimes you'll attach it to a surface like sandpaper. You know, it's just attached to a surface that you can use to shape things. So the characteristics of this, the cutting edges are very small. You're cutting with many edges simultaneously. So lots and lots of edges. It's not just one cutting edge. You have no control over the tool geometry. That's not entirely true. You have control over the form of the whole thing, but the individual cutting edges you don't have control over, because they are going to change all the time as it is cutting through. They're going to fracture. When they get dull, they fracture, and then it forms a new cutting edge. We'll skip that. Anyway, the reason that we can do this is because we're depending on these edges fracturing to sharpen themselves. If we use something else, the edge would dull, and then we would have to take it out and resharpen it. So by using these little materials and using a lot of cutting edges at the same time, they will fracture and sharpen themselves. So it can be free, where you just have it in a slurry. It can be on something that's flexible, like a belt or a disc, or it can be bonded into a wheel. Here are some pictures of things that we would grind with in a scanning electron microscope. We want these materials to be super hard. They need to be harder than the material that we're cutting. We want them to actually fracture in this case. So whereas in other things we've wanted toughness in the materials, in this we don't want toughness. We want the opposite of that, which is friability, meaning that when the pressure gets too high, it's going to break. And then we're going to get a new cutting edge. And we get to this, the coolest word of the entire quarter, which is the stuff that you get when you do grinding. When you grind a surface, you get this slurry. It's usually blackish. It has part of the thing that you're grinding, and it has all of the little broken off edges, and it's called swarf, which is just the best name of the quarter. So anyway, it's, you know, it's all downhill from here. We did swarf.
All right.
All right.
All done?
Class is over.
So swarf is really neat because it's just a good word, but that's all the little broken bits that are in there. You have to get rid of the swarf because we're cutting with all these little cutting edges, but they're really small. So if we allow the swarf to stay around, it will actually float the tool up off of the surface so that we can't cut anymore. So we have to be evacuating the swarf all the time. And we have dressing, which is shaping the overall form of the tool. We're not cutting the individual cutting edges, but the overall shape so that it will cut this the right shape. Yeah, there's a bunch of stuff that you can use that's hard. This is the second coolest set of words. Well, I don't know if it is, but anyway, there are funny words for all the abrasive machining, from snagging to grinding, honing, polishing, lapping. There's an odd set of terms that goes with it. And that's the difference that you get from a very coarse to very fine. So coarse is red, fine is green on here. Concrete grinding, horizontal surface grinders. These make really smooth surfaces on hard materials. So if you ever have a surface of steel that is ground, so very often on injection molds, they will take the mold surface and they will grind it to make sure it's absolutely flat so that you minimize the amount of flash that's on the edge of any of the parts by having it completely flat, at least to start with. And then a surface grinder, which you folks may use, I think you misuse it. You misuse a surface grinder in a later class, or a cup grinder to grind the pins for the molds that you make in the plastics tooling class. Okay. And then this is a diamond lap, which is just another way to do this. So this is one where the diamond is either in the surface or you squirt it onto this with the slurry and you use this to make things flat. We used to have to do that all the time when I was doing diamond turning because we needed the back of our parts to be super flat so it would stick to the vacuum chuck. 2 to 5% of the grains are cutting at any one time. All the rest of them are just there. They're a little bit higher. They're not taking any of the stress. So you have 2 to 5% of the grains cutting. And then once those get a little bit dull, the pressure will get too high. They will fracture. And then another 2 to 5% of the grains will step in to help out. If you have giant grains, they cut very quickly and they give you a poor surface finish comparatively. If you have really small grains, they cut very, very slowly, but they give you a better surface finish. And so what we do with these processes is we start out with something coarse and we move to fine, just like you do with sandpaper, because sandpaper is an abrasive. We don't care about that, and we're not going to do something with that right now. The thing that we don't know with these is we don't know what the shape of the cutting edge is, but we have a good idea that the cutting edge is very negative rake angle. Because if it has a positive rake angle, like is shown in this first one, you'll notice that that is a very thin edge out there. So it will dull and break off super quickly. And so almost all of the cutting is done by negative rake angle, highly negative rake angles. That's okay because the materials that we're machining are very, very hard. And so we need to take our rake angle and make it negative so that the surface, the other angle, the shear angle will lower itself down so that the material can shear well and be cut well. If you have something like glass or ceramic and you machine it with a positive rake angle, it's not good in tension, which a positive rake angle does, and it will blow out big chunks out of the surface. So let's say, well, this is what it looks like. If you look in a scanning electron microscope and you look at a ground surface, you will see that at some level, close enough down, it will have all of these little tracks that were just where it was dragging through the material. And then an event happened where it broke off the end of that piece that it was cutting with, that little grain, and then it goes on to cut with other grains in other areas. You can see this one also died right there, and then it left a big chunk of something in the surface, so that would not be very good grinding. But at some level, you'll be able to see this in all grinding. Okay. So things just for practicalities of grinding. Grinding is pretty dangerous because you are using a wheel that would like to come apart if you cut with it incorrectly. So wheels are designed to be cut with on the side or on the face, generally not both. There's a way to use the wheel, and if you use them in the wrong direction, they can come apart. There are some videos here that you can watch if you want to. One of them is just the wheel that has a flaw in it, and they spin it up to speed and it blows up. It has a guard around it, so it's really important anytime you're using a grinding wheel to have all the guards in place that go with it. There are lots of things on the interwebs of grinding wheels blowing up and getting stuck in people. We're not going to watch any of those because they're not very pretty. There's also a technique, if you are replacing grinding wheels, you can take the grinding wheel and you thump it on the side with something that's metallic, and if it rings, you can tell that it's good. And if it goes thunk, then that means that it has a crack in it, and it stops that, that oscillation that is the ringing that you hear, and it stops that from happening, and so you can tell very quickly without even putting it on the machine that it has a crack in it and it's not safe to use. You should also watch that Lazy Machinist videos because he has the Little Monkey song at the beginning and end, which is bizarre. He's just a crazy Canadian guy. Other things that, yeah, the Little Monkey song by, yes, anyway, that Lazy Machinist. We already did water jet. Water jet is just a free abrasive process, so the abrasive is happening in a stream of water very quickly. And also if you go outside and you do grit blasting, which we tried to do, but the grit blaster was not working, so we just air blasted things for a long time. That was sad, but anyway, we tried. Okay, so let's say you wanted to make a microscope. I'm sorry, a telescope. And you wanted to make one of the biggest telescopes in the world. You would go to the University of Arizona and you would go underneath their football stadium because that's where the microscope lab is for, I don't know, probably a third of all telescopes that are built in the world are built in the basement of the football stadium at the University of Arizona. And it's a pretty dang cool process. So this is an oven. It is a rotating oven. It's about 35 feet across. And so what you do is you start out by building up in the oven a bunch of ceramic hexagons. So the purpose of the ceramic hexagons is to lightweight the mirror, because if you made an entire mirror fully out of glass, it would weigh too much and it actually deflects itself. It's too hard to support it to keep it from deflecting itself. So you make all of these ceramic hexagons and you put them in there. You can see how big it is compared to them. And eventually, when you finish, it will look like this. So that's a lot of ceramic hexagons completely filling the inside of one of those ovens. Then you get some Inconel bands. Remember, Inconel is a material that does not, it has a very, very low coefficient of thermal expansion. So when you heat it up, it's going to keep these all held together and not allow them to expand apart and glass to flow, not much glass to flow down in between the hexagons. Then you go and you hand pick 41,000 pounds of high quality glass. You have to inspect all of the glass that you put in there to make sure that there aren't any defects in the glass. And you place the glass in there in as even a layer as you can. Okay, that's what it looks like when you're finished. And then you have to lift the person out of the middle, I guess. So they're about to do that. Then what you do is you put the lid on and you turn on the heat and you start to spin the whole thing. So this mirror was spun at 6.73 RPM. And the point of spinning it is that the glass will flow to the outside edge, so it will give you the a rough outline of the shape that you need. And so if you need a closer focal length, then you would spin it faster and it would have a deeper trough in the middle, more glass slung to the outside. If you need a further focal length, then you turn it slower than that. So it is relatively quick, actually. It only takes 1 day to melt the glass. This is the only fast thing in the process. So it takes 1 day to melt the glass, and then you cool it down for 4 months. Because if you cool it faster than that, the glass will explode. And so you take 4 months to cool it down, you keep it turning 6.73 RPM, you cool it down for 4 months. All right, great. Now we're ready to make it. So what we're gonna do is we're gonna start by polishing the back. We take the thing out, we flip it over, we put it in one of these machines, and we start to grind and polish the back. The back is the side that we don't care very much about, and so it only takes 6 months to make it flat. So very, very small abrasives. They will take 6 months to make the back absolutely flat, and the purpose of that is so that they can put supports on it so that they can hold it when they flip it over. When you put it, you flip it over, then you need to generate the shape on the front. And remember, we did the rough shape with the spinning. So after that, you just need to make the absolute perfect shape to it. That takes about 4 months. After you've done that, it has those little drag marks in it that we saw in the scanning electron microscope image, and you need to get rid of those. So what you do is use even smaller abrasive, but in this one, it's not going to reshape the mirror. All it's doing is removing those little drag marks by making tinier drag marks in it. So there we go, 2 to 4 months of doing that. And so after only a year and a half or something, you will have one telescope mirror. And the most recent telescope, what is that one? They keep upping their names. I think it's the very large telescope is the one that they're making right now, and I believe it has 64 of these, something like that. They're a little bit smaller than this one, but sort of on that scale. So anyway, it's weird. It happens underneath the football stadium at University of Arizona.
Can they make more than one of these at a time?
Yeah, they have a couple of ovens. I mean, it's a football stadium, so there's some space to it.
Yeah.
The reason that they do it there is because there's very little around the football stadium that goes on during the week that would shake this process. And then if you're gonna have a football game, you stop all the machines because the people around it will shake it too much and cause the surface to not be very good.
It's crazy.
Yeah.
Do you know how long they've been like working on this 64 lens telescope?
It takes them 10 to 15 years. Well, there's probably 10 years of design, 10 years of getting funding, and then another 10 to 15 years to manufacture it. So that's all going on the top of a mountain in Chile, or Peru, one of those two. Anyway, it took them, they took the entire top of a mountain off to be able to put the telescope there. So they did a bunch of blasting and took the whole section of top of the mountain off and then putting the telescope in place. It's pretty awesome. And yeah, seeing things about how they design those telescopes, I applied to be the telescope precision engineer at Mauna Kea in Hawaii, but they didn't select me. Really bummed. Yeah.
But now you get to be our teacher.
I know. I think it would have been fun to be in Hawaii and be the only person who wore a down jacket to work every day. All right. So, yeah, that's how you make a telescope, if you, or yeah, really big telescope if you need to. Oh, yes.
How do you transport a lens this size?
Yeah.
Very carefully.
Like,
So you put it, so that is actually one of the limitations on the size is how you can transport it, but you put it diagonally on a truck that's oversized, and it has to be an air ride truck, and you put a bunch of structure around it so nothing can run into it, and you drive slowly and honk a lot.
All the way down to Chile?
Well, you drive as far as a boat, and then you put it on a boat. And
Why a
then,
boat, not a plane?
Cause it's too big and too heavy for a plane.
I'm also like one of the big
The Russians blew up the last one of those, so, yeah, those are all, the really big, lift planes are all Ukrainian, and the Russians blew up the two really big Antonov 224s.
Now we can't transport our telescope mirror.
Well, we can put them on a boat, we just can't fly them, so you have to plan ahead. Okay, if you have lab today, remember we're in ET 262, and if you don't have lab today, you should find something else good to do with your afternoon, and it should involve path planning, because that is a good thing to do with your afternoon, now that you know how.
So you went today?
One, yes.
No, I thought you said two.
No. No, 1 o'clock.
Sorry, fitting the message.
Oh, yeah, I guess I do. Thanks.
I told you, babe. I saw all my friends there, sorry.
No,
I I just do it flexibly.
Do you want to take care of drill bits for you?
I know, me.
And then, did the MFGE2 town go like honey?
I know, I cook it honey all the time.
Hey Mac, hand me your drill bit, please.
Nope, I have no qualms.
Call people pet names.
Yeah,
I don't think I do it to Dave.
She called me, like, Dave.
Yeah, I just did that to Dave and he was like, what?
What?
Yeah.
Put it on our fridge.
Oh, yeah. Hey, how's the midterm grading go?
I'm through 3 of the 4 pages, and it is okay.
How are we doing? How are we doing? Uh-oh. Not what you like to do.
There's a reasonable amount that's going relatively well.
Has anyone gotten like 100%?
There's at least one that is very close.
What are you talking about? I don't have it.